homework due Friday, right? Homework, 4 problems, no circular beam. I bumped that to later, so. Okay, all right. So then, yeah, exam coming up next Wednesday. We already talked about that last time, so nothing new there. We'll just continue then with this lecture on strain energy, and then today we'll start the lecture on Castigliano's modified theorem for straight beam deflection calculations. We probably won't get through that whole lecture. I anticipate we'll probably stop before the indeterminate beam example, but we'll see how it goes. All right, so last time we left off after just doing this short example, demonstrating the application of calculating strain energy in this column. So that's just a uniaxial condition. Now we'll look at a slightly more involved problem, which is a beam with a distributed load on it. So here we're going to assume that there's no axial load, or I should say there's no axial force, right? We can see that there's no axial load. So based on that, we'll assume axial force is equal to 0. We'll also assume that the beam is very thin, which means we can neglect the effects of shear. So then if we only consider the contribution of bending or flexure to strain energy, then all we need is the moment. So in order to determine the moment in the beam, we'll make a cut and derive our moment equation. So taking the right side of that cut, right, we've exposed all the internal forces, but we just decided we were going to assume that F and V are equal to 0 for the purposes of determining strain energy. And so we sum moments about the cut. We'll get our moment expression in terms of Q, L, and X. So say M of X is equal to negative Q naught times L minus X. So we're just summing moments about the cut. This is the resultant force. And then we have to multiply it by the moment arm, which is L minus X over 2. So that simplifies to negative Q naught times L minus X quantity squared over 2. So we'll then evaluate the shear strain, the strain energy, capital U. That's going to be the integral from 0 to L, right? We're integrating along the length of m squared over 2EI, or 0 to L, plugging our expression in now in terms of Q and L and X. All right, and we're squaring the moment term, so we have Q naught squared, and then the quantity L minus X is to the 4th, divided by 8EI. So the 8 is coming from the 2 in the denominator here, and this term squared in the denominator as well. So that's negative Q naught squared times the quantity L minus X to the 5th after evaluating the integral, divided by 40 EI, and that will be from 0 to L. So U is going to be negative Q naught squared. I'll just evaluating this integral, so I'm going to skip that part. So negative, the result, all right, the end result will be Q naught squared times L to the 5th over 40 EI. So that's just due to bending, right, flexure. If the beam had a wider cross-section, we wouldn't be able to neglect shear. Or if it had significant depth with respect to the length, then we also wouldn't be able to neglect shear. So in that case, let's see how that would affect our calculation. So I'm just going to note here, if the beam has a wider cross-section, or a significant depth, let's see, or a significant depth with respect to length. So that doesn't mean a larger depth than the length, but just more significant, right? The way it's sketched now, it's pretty long and slender with respect to depth and length. So it's reasonable to neglect shear, but otherwise you would need to account for shear. So that we would need an expression for V in terms of Q. So that would be Q naught times L minus X. Just going back to our free body diagram here and then summing forces in Y. So then the strain energy would be the integral from 0 to L of our moment term, which is Q naught squared times L minus X quantity to the 4th over 8EI. And then we would also have the shear term, which is the K. That shear shape factor is actually the Greek letter kappa. I've been saying K, but it's technically kappa. So that times Q naught squared times L minus X quantity squared over let's see, 2GA. Yeah. And so evaluating that integral, we would get Q naught squared times L to the 5th over 40 EI as before, but now plus shear shape factor times Q naught squared L cubed over 6GA. So there is a certain length or depth to length ratio where the shear contribution to strain energy actually will dominate the deformation, right? And in the homework that will be related to this lecture, you will investigate that situation. So you'll look at where that point is, where the shear contribution will become more dominant, right, than the bending component. So, yeah. Questions?
Like a goal seek.
Huh?
Like a goal seek.
Yeah, you'll need to probably do a solver like that in Excel. So, yeah.
Are there any like beams that we would actually deal with where we could ignore the shear, or is that just like to help us develop this equation?
Oh, sorry, say that again. Are there
like, would we actually ever be able to ignore the shear contribution to strain energy, or is that just a hypothetical to help us develop the equation?
So yeah, for beams that are really long and slender, the shear contribution will be negligible, essentially, to strain energy. Yeah, and so that's what you'll see when you go through the homework assignment. Yeah, so you'll see how quickly, right? So basically, what you'll find is without spoiling too much, for a low, let's see. L over D, yeah, for a lower L over D, right, so that would represent a beam that's, pretty short compared to its depth, or, not long and slender, then your shear contribution will dominate. And then at a certain point, shear and moment contributions will be equal. Beyond that, the moment contribution will dominate, and pretty quickly it becomes the point where the moment contribution is completely, almost completely 100%. So, yeah, that shear contribution very quickly diminishes after that point. Yeah. And this concept is, we're looking at it on a scale of a beam, but this can also be applied to a larger scale, like tall buildings, for example. Very tall buildings tend to behave more like cantilever beams in, lateral excitations like wind. So when they are swaying back and forth, if they're very tall, such as the Burj Khalifa in Dubai, right, the current tallest building in the world, that building, when it deflects, its first mode shape is essentially a pure cantilever. And so the deformations, or the energy dissipation associated with that movement, is primarily due to axial deformations, which is the axial from bending, right? And whereas you have other buildings that maybe have a significant amount of shear deformations. An example of that would be the Sears Tower in Chicago, where you have a lot of frames. It's essentially a framed tube, a bundled framed tube structure. There's a lot of shear lag that's lost in those moment frames as they flex and shear throughout the length of the building when it's moving back and forth. So that building, because there's a lot of shear deformations, right, you wouldn't want to neglect the shear contribution to that. So that's just kind of thinking about it on a bigger scale, what it is. But yeah, so it's not as simple as just the depth and length ratio in larger contexts, but that is a big player in what's going on. Yeah. But yeah, what it's really tied to is the deformation mechanisms that are dominant in the structure. So for a simple cantilever beam, the longer that beam is, the less significant shear becomes.
Right.
Yeah.
But then in like a short little like squatty like 2-story building, it's just like, it's not like leaning like a cantilever.
Right.
It's just like shearing basically. Exactly.
Yeah. Yeah, you have a lot of shear behavior going on there. So, yep. All right, so now applying this concept to circular beams, we're going to start with the general equation for strain energy that includes normal stress and shear stress, and then we will sub in our equations for normal stress and shear stress that we derived previously for circular beams. So start off with our strain energy is 1/2 times the integral over the volume of normal stress in X times normal strain in X plus shear stress in the XY plane times shear strain in the XY plane. and then subbing in our expressions as they relate to circular beams, we would have, let's see, well, not quite yet, sort of, we'll start subbing some things in, and then we'll sub the rest in. All right, so we got normal stress squared over 2E plus shear stress squared over 2G. And then integrating over the volume, all right, so this is where the first substitution related to circular beams comes in. Instead of dx, we're going to have r times d theta. All right, so that's the equivalent of dx. And then we'll have dA after that.
Is that 1/2? Oh, you just integrated it.
Yeah, I just brought it inside, yeah. And so now we're going to make our stress substitution. So normal stress in x is m times y over a lowercase e lowercase r plus n over a. And our shear stress, we're just going to take the average shear stress, V over A, and that's okay for circular beams. In the context of strain energy, at least. Really, in general, since we said circular beam shear stress is pretty negligible, so then we have our strain energy integrated over the volume, 1 over 2E, that's capital E, and then in parentheses, my over a lowercase e lowercase r plus n over a, and that gets squared, plus the shear shape factor kappa over 2g, and then v over a is squared. And then we have r, let's see, how did we, I just gotta make sure I'm being consistent here. In circular beam equations, all right, yeah, so I have a correction to make here. This should be d phi, not d theta. I want to be consistent with how I did it there. So this should be r d phi. Yep, that's the shear shape factor, kappa. So that is part of the, let's see, where did that come from? Shear shape factor, we did that in the last lecture.
Is that supposed to be part of the shear term though?
I understand what you're saying, and no, but what am I missing something here? So it's part of the integral, let's see. So if we go back a few pages here. So this is equal to that. So we brought it down. Yeah, so shear strain is basically, this is what we're using right here, where this is the shear shape factor, kappa. Yeah. So it's not, it doesn't show up with the shear stress. It shows up after you make the substitution. All right, so then making some more integral substitutions. And really what I'm going to be doing here is identifying the items that are going to be variables within this integration. So we're going to end up with integrating a y term over the area. And we're going to be making the substitution Rn minus R is equal to y. So when we see the integral of y showing up in this equation, we can say that's the integral of, let's see, that'll be over the area of Rn minus R dA, which would be Rn times area minus the integral over the area of the variable R. All right, and this integral is going to be equal to capital R times A. All right, remember, capital R is the radius from the center of curvature before loading to the centroid. So that's Rn minus capital R times A. And the difference between the neutral axis radius and the centroidal radius we defined as E. So this would evaluate to negative E times A, and that's lowercase e. And then the second integral substitution will end up from this term, quantity squared, we would end up with a term that has a y over r in it. So again, making this substitution for y, we would have integral of Rn over r minus 1, which is Rn times the integral over the area of dA over r minus a. And this integral would evaluate to area over Rn. So this term would become Rn times a over Rn minus a, which is 0. So that helps to simplify things a bit. And then the third integral substitution, again coming from this moment term being squared, or the normal stress term, I should say, being squared, we would end up with a y squared over r to integrate. And y and r are both variables, right? So we're making this substitution so that we only end up with one variable inside our integral to think about. So integral over the area, then making that substitution for y, we get Rn squared minus 2Rn plus r squared over r. So that's Rn squared times the integral over the area of dA over r of minus 2Rna plus the integral over the area of r dA. And this first term would evaluate to Rn times A, And this last term would evaluate to capital RA. So this whole thing would simplify to lowercase e times a once you work it out. All right, so that was the last one. So then we have an expression for our strain energy. For a circular beam being integral of m squared over 2a capital E lowercase e d phi plus integral of n squared times capital R over 2 capital E a with respect to phi minus the integral of m times n over capital EA with respect to phi plus shear shape factor kappa, I forgot the integral, integral of kappa times v squared over 2GA. And then in this one we have R d phi. Now this third term here is a negative term in the expression because a positive moment will compress the centroidal axis, which is where the normal force N acts. So the work done in that situation is negative, right? In all the other cases, the work done would be positive. Sorry, my iPad is thinking for a moment. I don't know why. Let me try something. Okay, I think that fixed it. Oh, was it updating? Saying no signal. That's not correct. All right, bear with me. I'm gonna turn that thing off and back on. See if that corrects it. I love technology sometimes.
Are these values for moment and shear, do we evaluate those like at their maximum or at like the point of interest?
So,
Are we looking at strain energy typically over like the whole?
yeah, so over the whole system, right? So it would be similar to this, well, you can't see it right now, but similar to the example that we just looked at with the cantilever beam, because we're integrating over the length, right? That's what that final equation is representing, integrating along the length. So it should represent not just the maximum shear moment, but the distribution along the length.
Gotcha.
Yeah. So it should be fully representative. This might be a short class. Actually, no. What I'll do, if this can't work, I'll just switch to the doc cam and I'll show you my completed notes and just talk through them. and then I'll post them or something, because this is really inconvenient. All right. Well, I don't know why this wouldn't be functioning properly. I can see that this is on. It's just not displaying. It is connected. Everything's connected. Yeah. No, there we go. Okay. All right. So I was just about to write this note about why this is negative. All right, so questions on the strain energy? Okay. All right, so now we'll start talking about Castigliano's modified theorem and apply it to straight beams. So, who's familiar with Castigliano's theorem from other classes? Anyone? A few? Okay. So, may or may not be the same as what you've seen before, because we're doing a modified theorem approach, which uses basically the Maxwell-Morse theorem and makes a substitution or some assumptions for the partial derivative of moment, or whatever you're considering with respect to a specific applied nodal force or moment. So you'll see that as we go through. But if it's a little bit different from what you've seen before, that's probably why, because we're doing a modified approach. So I don't know, did you do a modified approach before, or?
I can't really remember, but I feel like we did do a modified, or what was it modified? I don't know.
Okay.
Probably.
All right, no worries. So yeah, it probably was, just because I think we need to modify it for practical purposes, really. But yeah, so basically, for a beam in bending, right, we looked at this just now. Here's your strain energy, and this is just the contribution of bending to strain energy. All right, so this is just from bending. If we want to express that moment in terms of applied forces and beam reactions, which is often necessary or convenient, then the modified Castigliano's theorem will define a deflection at a specific point, VI, as being the partial derivative of strain energy with respect to a force at that same location. We'll represent that force by P. That's also often noted with the lowercase delta. And the rotation at a specific point, I, can be represented as the partial derivative of strain energy with respect to a moment at that location. So we'll define MI here represents an applied moment. PI represents an applied force. and these are all at a specific point, noted I. So if we consider a cantilever beam with an applied moment at the mid-span, and we want to find the vertical displacement at B, looking at this relationship, right, we don't have an applied force at the point where we want to calculate deflection, right, or B is over here, right? We don't have an applied force at B. So that means we need to place a fictitious force at that location to apply this method. And then we will eventually drop that out of our consideration, right? Is this sounding familiar?
Yeah.
Okay. All right, so we're gonna apply a fake force. We'll call that capital Fi. And I'll write what I said a moment ago. No applied force. All right, so now, since we have two regions where moment expressions will, two different moment expressions will apply, we're going to establish our moment equations for each region. All right, so we'll first take a cut through region 1, and that's what we see down here, the free body diagram to the right of that cut. So, we are exposing internal forces at the cut. All we're interested in is the moment. So I'm going to call that M for region 1. And our X will be measured as positive from the left end. So if we sum moments about the cut, we get our expression for moment in region 1. So that's going to be negative M1, a function of X, plus the applied moment M0, plus the fictitious force Fi times moment arm L minus X is equal to 0. So the moment in region 1 as a function of X is equal to M0 plus Fi times L minus X. Then for region 2, we just make a cut between the midspan and the free end. Expose those internal forces and moments. We're only interested in the moment. We still have that applied force. I forgot to draw it on the free body diagram above also. All right, the fake applied force. X is still measured from the fixed end, the left end. So summing moments about the cut. We have negative moment in region 2 as a function of X plus fictitious force Fi times L minus X. Moment arm is equal to 0. So our expression for the moment in region 2 is the fake force times L minus X. Now, interpreting that to reality, right, we know the real situation doesn't have a force here, so there should be no no moment in region 2, right? That moment should be 0 between the midspan and the free end. And so knowing that that is going to eventually go away and it won't represent the physical situation, that makes sense. The reason we're doing this is for the purposes of obtaining the partial derivative in this process. So we need this relationship to get the correct partial derivatives in both of these equations, right? So you'll see as we apply this on the next page here. So we're after the deflection at B. All right, so we can write delta B is equal to the partial derivative of strain energy with respect to the force, fake force Fi. All right, so that's going to be 1 over EI times the integral of the moment times the partial derivative of the moment with respect to the fake force. So that'll be 1 over EI times the integral from 0 to L over 2, right? We're going to break it up into the first region and the second region since we have two different expressions for moment. So then the first integral for region 1 will have our m1 times the partial derivative of m1 over with respect to Fi. And then our second region integral will be from L over 2 to L. And we'll use our expression for moment in region 2 for this term. So then plugging in our expressions for those moments, we have 1 over EI times the integral from 0 to L over 2 of m naught plus Fi times L minus x. And then the partial derivative of that expression with respect to Fi is just L minus x. And then we have our second integral from L over 2 to L. And that's just going to be Fi times L minus x times the partial derivative with respect to Fi, which is L minus x again. All right, so I'll note this guy here is the partial derivative of moment in region 2 with respect to Fi, just as this term here is the partial derivative of moment in region 1 with respect to Fi. Now, since Fi is a fake force, as we talked about a moment ago, and it's not actually contributing to strain energy, we can drop it at this point after those integrals have been set up, right? So once we've obtained this part and set up the integral, we can then get rid of the actual Fi terms in that integral. So then our deflection at B is m naught over EI. Evaluating the integral after removing FI from that expression, we'd have in brackets negative quantity L minus X squared over 2, evaluated from 0 to L over 2. All right, so the region 2 integral doesn't amount to anything, right, since this term becomes 0. So this evaluation gives us 3 over 8 times m naught L squared over EI. Now, one way we can check this is to find the deflection and the slope at the midspan, and then extrapolate, since we know that there won't be a change in slope between the midspan and the free end. We can then determine what that value will be at the free end based on the values we get at the midpoint. So we'll just demonstrate that. So the slope at midspan would be the partial derivative of strain energy with respect to the applied moment, m naught. Since there is an applied moment there, we don't have to add a fake one. We'll just use the applied one. So that's 1 over EI times the integral from 0 to L over 2 of the moment in region 1 times the partial derivative of that moment with respect to m naught. And then we have our region 2 expression. So that's L over 2 to L times the moment in region 2 and the partial derivative of that moment with respect to m naught. So it's important to note that here with this evaluation, we are no longer using the expressions for moment in region 1 and 2 that we found on the previous page, because those are all with respect to a fake force applied at the free end, right? So this was specifically for finding the deflection at B. Now that we're calculating the slope at the midspan, we have an actual moment there. So our moment expressions will just be, for region 1, it's just going to be m naught, and for region 2, it's going to be 0. All right, so note, now m1 is equal to m naught, and m2 is equal to 0. Right, no Fi or Mi needed. Or I should say, yeah, no Fi needed. Technically, the Mi is m naught, right? So from that evaluation, we get the slope at midspan is equal to m naught L over 2EI. And I know we're out of time, so we'll finish that up next time and verify the slope at B that we calculated here. And then we'll apply it to an indeterminate problem. So, all right. All right, we'll see you all on Friday. Oh, 1 second. Yeah?
Sure. Because I thought that for this first part of question 1, it'd be easier to calculate the stress with like force over area instead of like the moment y over I. But I think you get a different answer if you do it that way than if you just do force over area.
Okay, remind me which problem this is. This is the composite section.
Yeah.
Okay, so so no, force, because it's bending, right? So you need
So
to
I
use
need
the
the
bending
bending.
stress equation, yes, yeah. Yeah, cause you're saying for that force over area, you're taking the Q?
That would be the normal, so that.
Yeah, that would be the normal force in the Y direction, which we're neglecting in this case, yeah. Yeah. Good
The
question.
next exam is, no, it's just on the exam,
Okay,
is gonna be
Wednesday.
Wednesday, but over FEA.
Yep, starting with FEA, and going through shear center and skew load. So everything between FEA before circular beams.
Okay, so the stuff that's on homework 6 is on the exam.
Yeah, the homework that's due Friday will be on the exam. Yeah, so I'll be sure to post the solution for you guys before, in advance of the exam.
Awesome.